Hi. Some of you may recall a while ago we had a look at an infrared emitter and detector beam pair. So this is a pair of devices typically used for security applications. You'd normally attach it to your alarm system or some kind of CCTV system, and if someone breaks the beam, it will trigger an alarm signal, or it might cause your CCTV to start recording, that kind of thing. And I wanted to implement this on my front gate so that if someone walked through the gate, it would cause the alarm in my house to chime and let us know that someone was approaching the front door. Now, I did actually implement this, so I've got a pair of detectors on the gate, but I modified a sensor for my alarm system. I have power to each side of the gate, but I didn't run any alarm cable to it at the time, so I need to use the wireless system, and that isn't quite working as well as I would have liked. There is a little bit of a delay, and also it triggers on the wrong edge, and there doesn't appear to be a way that I can fix that with the detector that I've modified. So what I wanted to look at today is these little RF receiver and transmitter pairs, which I bought on Amazon quite cheap. It seems to, you can get these in a variety of different frequencies. This one is the 433 MHz, so this should have really quite long range. And to support these little PCBs and actually have it in a way that is quite robust in my house, I got some PCBs made at PCBWay. So here we've got the box. And inside the box we've got the PCBs along with a free sticker. And because of the size of these boards, we can get these 2-layer boards for $5 for 5 PCBs. And I know a lot of people often complain that the shipping costs are quite disproportionate to the price of the PCBs, but really that's only if you're in a rush. Obviously DHL are going to charge $22 for your shipping. FedEx is not that much off, $17, but there are some other options on PCBWay's website. So we've got PCBWay Express, which is about 3 to 4 weeks, and that's coming in at $10, so starting to become a lot more affordable. There's a slightly quicker option, so PCBWay Express International Priority, 12 to 15 days for $12, and then if you're really not in a rush or you want to save money, there are the China Post and e-packet options. And China Post, although it says 30 to 90 days, depending on the time of year, it can get to you within about 2 weeks, I found, and then the shipping cost is only $5, meaning you can get some prototype boards for only $9, so really quite economical for these high quality boards. And looking a bit closer at the PCBs, you can see what we've got here is the transmitter board. The idea is that the transmitter PCB solders into this row of pins here, and then we've got an interface to the receiver module on the infrared detector beam pair, and then we've also got the 12-volt input to power this transmitter. Now oddly, on this board there is nowhere to actually solder the antenna. It appears on pin 1, but they provide you with this antenna, and it's not really an easy way to solder this onto here and have it looking neat. So I've just put a trace out here from pin 1 onto the PCB so that we can solder this antenna in here. Similarly, we've got the receiver board, and here is the receiver module. This one does actually have a place for the antenna to be soldered in, so at the top there we just solder in this antenna and that sits up in the air like that. But we've got our 12-volt input on a terminal block from the alarm system to a 78LO5 5-volt regulator because the receiver needs a 5-volt supply, and then our outputs here to 4 optocouplers because these are logic outputs, but my alarm system needs open-close contacts, so we're effectively emulating that with a row of optocouplers. So when I was looking for these modules, I didn't really find a huge amount of supporting information about them. What I would like to know in particular is how they transmit that a signal is active or not active on the input, because it has 4 inputs here labelled 4321, and it's basically echoed on the 4 outputs from the receiver board. What I don't know is whether it's transmitting all the time, whether it only transmits when there's a change in the logic signal, or whether it transmits all the time only when the input is active. And if it's transmitting all the time, that's not ideal. If it does that, we may need to think about a slightly different solution, or maybe AC couple the input. So I'll put some series capacitors here so that we can just trigger that an event has occurred on the sensor, because I don't need to know that something's there all the time. I just need it to chime when someone breaks the beam. So we're going to solder up these boards, check everything works, and then find out what the operation actually is. So here is the beam pair. This is the transmitter on one side, and that just has a pair of infrared LEDs and some electronics to modulate those on and off. And then on this side we have the receiver. and that has a pair of photodiodes with some lenses, some receiver circuitry, and then also in there is a modified transceiver for my alarm system that relays that to the alarm when the switch contacts are closed. And then just at the bottom there we've got power coming in from that box, which then receives power from the house. So here's our receiver, and you can see we've got a pair of lenses here. These have the photodiodes in, and then this is the actual receiver circuitry. And these ones are actually from Banggood. I think they cost about $30 in the end. I did buy some expensive TACX ones, but they were just too big and bulky for what I needed. So I went with these to see how they were, and they seem to work really nicely actually, especially across this relatively short distance. And then you can see we've got a pair of wires coming out of here from the contacts, and that goes to one of these Texacom micro contacts, which I actually modified for this, but this is what isn't quite working as well as I would have liked. So it doesn't trigger until whatever was present has been removed from the beam. So today we're going to try out some Kester solder. I managed to get this from Amazon.com. It's not really sold in the UK, but a lot of people mention that the Kester solder is really nice, so let's give this a go. And to start off with, rather than capacitors, we're just going to put some resistors in these pads here so that we have a straight DC path into the inputs on the transmitter. So first of all, what we'll do is we'll just tin one of the pads on each component so that we can solder in those 0805 parts. And I've just moved to the microscope here to make it a little bit easier for me to see what I'm doing. And don't worry, I haven't forgotten about the ring light project. I will be finishing that off very shortly. So a short while later, and we've got two working PCBs. One thing I realised when I soldered up this PCB is I'd completely forgotten to implement a impedance controlled trace for the antenna. So what I'd planned was pin one here, coming out here, and then I'd solder on this antenna, and you'd think at 433 MHz, even without the impedance controlled trace, that we might not have had any significant effect, but it completely stopped it working. So what I've ended up doing is cutting the pin on the pin header and soldering the antenna directly to the pad. It looks a little bit crap, and it's a shame that they didn't provide a dedicated pad like they have done on the receiver. You can see the antenna soldered up here. But, you know, for something low cost like this with a tiny PCB, that's about all that can be expected. So the way that these work is you've got 4 inputs on the transmitter, and when you apply a 0-volt signal to it, you can see you get a red light saying it's transmitting, and you can see there on the receiver board, you also get a red light to say that it's receiving that signal. Now, one thing that I've noticed is that the 4 inputs don't correlate with the same 4 outputs on the receiver board. They're actually all muddled up. So I've got an LED in position 4 here, but when we actually apply a signal to position 4, it doesn't illuminate. It triggers on channel 2, and then channel 3 on the receiver is actually channel 1, and then we've got channel 4 and then channel 3. So they're all muddled up, but really it doesn't matter so long as you then sort them out on your PCB layout or on your input so that they correlate in the way that you want them to. Now, I've only put 2 optocouplers on here because I don't need all 4 channels anyway, but that seems to be working quite nicely. What I want to look at now is, I think I know the answer already, but I wanted to see whether it was continuously transmitting the whole time that you had a signal present, because technically we're sort of using that channel all the time. What would be nicer is if it just gave a signal once or twice, enough for the receiver to see it, and then stop transmitting. Right, so let's see if we can see what's going on. So we've got the SDR receiver here set to about 433 MHz, and if we apply a signal onto one of these pins, you can see here we're getting a continuous signal at about 433.9 MHz. So that is continuously transmitting, and it doesn't appear to go into any other mode no matter how long you have that signal present. And then when you remove it, you can see it just stops transmitting. It appears to do the same thing on all of the inputs, so not really any difference that's visible here. So I think what we might end up doing is seeing if we can AC couple the input so that it only triggers on a change of signal. So what we've got on the PCB is effectively this circuit. Now there's not a separate pull-up resistor on the PCB, I think there's an internal pull-up in the transmitter chip, but what happens is normally it's pulled up high, and then when we apply our 0 volt signal to the input here, it pulls this signal low, and then that's what actually starts it transmitting. Now what we actually want to do is only trigger on edges. I'm not really bothered about the fact that the signal might be present the whole time. So I'm thinking we might put a capacitor in series here, and then when we short these two pins out, we get a brief amount of current flowing while that capacitor is charging up, enough for us to receive that at the other end, and then we will no longer get any transmitted signal. Now obviously in this configuration there's no means for the capacitor to discharge, so once you remove your signal and try and apply it again, nothing will actually happen. It will be a one-shot sort of trigger. So what we also need to add in is potentially some kind of discharge mechanism across that capacitor, so that when you remove the signal, that capacitor starts to discharge. Also what we need is probably some kind of series impedance, so that it takes a while for that capacitor to charge up, so we don't suddenly just get a signal that's too short for us to see. So we might need to play around with these values a little bit, but we can first of all work out the equivalent resistance here of this pull-up by measuring the current that flows when we short one of these pins to ground. So if we do that now, you can see about 25 microamps is flowing there, 27 microamps. So it's about the same in all of those, so about 25 microamps coming through here. And then we can work out the effective resistance by also measuring the voltage when it's open circuit. So let's have a look at what that looks like. About 3.3 volts. So we've got enough there to know what that equivalent resistor is. 3.3 volts divided by 25 microamps, the equivalent of about 132 kiloohms. The next thing we need to think about is this resistor here, which is here to discharge this capacitor. Now if the value of this resistor is too low, what happens is when we short these pins out, we've just got a DC path through that resistor. It'll pull it down low enough to start triggering the transmitter to start transmitting. So we need this high enough that it doesn't cause that to happen, and we've basically got a potential divider here with these two resistors, but we do want it low enough that it doesn't take forever to discharge this capacitor. So we can at a glance probably say that so long as the resistor here is about 10 times the value of this one, so 1.3 megohms or something like that, then we know that voltage is only going to be about 0.33 volts less than the signal when it's open circuit. But we can be a little bit more precise than that and just double check that is true. So we've got Ian's voltage source here, and I've applied this across these 2 points here, and you can see it's currently not transmitting. If I take this down to 2 volts, you can see it's still not transmitting, and sometime between 1 and 2 volts, that is where the threshold occurs. So yeah, when this node gets to 1.9 volts, that is where it stops transmitting, or when it starts transmitting. So I think there's a little bit of hysteresis on here, as you'd expect. So what we need to do is make sure that when we've got this resistor in place, the voltage at this pin is somewhere above 2 volts, and that should make sure it behaves as we expect. So running that number through a voltage divider equation, what we can work out is for this voltage to be at least 2 volts to stop it from transmitting under normal circumstances, we need a resistor at least 203 kiloohms. Now we're actually going to use something much higher than that, so we're not quite so close to the threshold. Using a 1 megohm resistor here gives us 2.9 volts, which is pretty acceptable. That's not going to cause us any trouble. So we've got our resistor here, 1 megohm. The next thing we need to think about is a series impedance here, because if we just shorted the input at this point, the capacitor would probably charge almost instantaneously. So we need to slow that down so we actually have a signal there for a reasonable period of time, so that the transmitter actually has time to transmit that. So the first thing we need to think about is the value of this resistor, and we have the opposite problem here. We need, when this resistor is present, we need the voltage at this point to be less than 1 volt so that we can actually start the transmitting on the transmitter. So running the numbers through the voltage divider equation again, we know that this series resistor here, the maximum value it can be is 57 kiloohms for this voltage to be less than 1 volt. So we can probably assume something like a 47k resistor, and then the next thing we need to think about is what this value of the capacitor actually is. And we can approximate it with the time constant, tau equals RC, and if we assume we want it to be present for about 1 second, obviously this is only up to a certain point in the charge of that capacitor, we know that we've got our equation here, 1 second equals 47k times the capacitor. So if we rearrange that, we can work out what the value of C should be. And C here should be about 22 microfarads, which I think I've got some 0805 parts with that capacitance, so that's probably quite a reasonable value. So you might be able to see in there, I've just soldered a 22 mic 0805 capacitor and a 1 meg resistor over the top of it, and that is attached to channel 4. And in this application I only need one channel. That was the easiest to get to, so that's the one that I have modified. And just to clarify what we've actually got now in the circuit, we've got this 132k weak pull-up inside the chip. This is not a resistor, it's most likely some kind of FET in there. Then we've got our signal to actually trigger the transmission, that's internal to the chip again. And then outside of the board is our 1 meg and 22 mic capacitor. And then separately to that, we've got a resistor in series with our alarm contacts of 47k or so. So that gives us a time constant through this resistor and this capacitor of about 1 second. But something to bear in mind is our time constant here for these two components, the 1 meg and the 22 microfarad capacitor, is about 22 seconds. So once we release that impedance here, it would take about 22 seconds for these two components to fully discharge this capacitor. So it's not going to be able to trigger every second, there's going to be some recovery time. It doesn't matter in this application because we're only looking for someone walking past the sensor on the gate, but that's something to bear in mind with a circuit like this. So we've got two 22k resistors in series here. This is just what I quickly had to hand. So we can try to see if this actually works. So we've got one on one end, one on the other. And there we go. So it's now stopped transmitting. You saw it transmitted for about a second and now nothing. So that appears to be working as intended. We saw it receive it here successfully, so that was enough time for it to trigger. And you can see here we've got that recovery time, so even though I'm touching the resistor now, it's not transmitting, so there's a little bit of a delay there, but that appears to be working exactly as intended. We'll give it a little bit longer just to make sure it can re-trigger, but I think the next stage now is to actually try this on the sensor on the gate. So here we go, let's try it one more time. There we go, so triggered, transmitted, and then stopped again. So that appears to be a success. So there we've got it wired up to the 12 volt terminals here coming from the power supply in this box. We've got it hooked up to the normally open terminals on the contacts for the receiver. And then we've got the PCB here, which is actually just going to mount to the back of the sensor. You can just about see the LED on the board here. So when we break the contacts, there we go, we see the flashing red light briefly to say that would have transmitted that signal. Right, so I've got my wife out there ready to break the beam. We're about 25 meters away in the lab, so let's see if it works. Okay, ready? And there we go, so we can see the LED illuminating there, and we can also see that pulse on the SDR receiver. So that seems to be working nicely. So that's a quick look at these 433 MHz transmitter and receiver PCBs. These ones were branded Kaya chip, and they were from Amazon in a pack of 3 pairs. And these ones were quite nice because a lot of the transmitter and receiver pairs, the transmitter seems to be in a key fob, whereas for the type of projects that we might want to do, this type of form factor where you can solder it into your PCB is a lot more suited. So these were quite nice, but I think in some future project we may look at using a dedicated 433 transceiver chip, integrate it with a microcontroller, and then we can have a bit more control over what we're transmitting. But I think for the price, these are really nice little transmitter pairs. Also, a big thank you to PCBWay for supplying the PCBs for this project. Do consider visiting their website if you're looking for some PCBs. They've got a lot of services on there, and quite a variety of different PCB technologies, so really worth visiting if you are thinking about having some prototype PCBs made. So I hope you found the video useful, and until next time, thanks for watching.